Okay, hello everyone and welcome to the Midas Civil webinar. My name's Adam Kane. I'm going to be taking you through proceedings today. I'm just going to take a couple of seconds just doing a bit of a sound check and making sure everybody's in the room. Got a good turnout, so if some of you could raise your hands or just place a comment in the comments box. And we'll start in about 10 to 15 seconds. Okay, I've seen a couple raised hands and you've passed some comments in the box, so I'll begin. I'll just start again. So this is the Midas Civil webinar for dynamic analysis of footbridges to Eurocode standard. My name's Adam Kane. I'm the technical support engineer for Midas in the UK, based in Hammersmith. Our telephone number and email are up on screen, and if you do wish to contact us, please use those details provided. Obviously, if you have any problems, then please by all means phone us now. So just go through some of the housekeeping rules. First off, you can maximise the screen. Secondly, if you can't hear me, it's more than likely, or if I'm slightly muffled or on a low volume, you probably have to turn the volume up or change it from mute. If you want to maximise it, then please click on the double box up in the top right hand corner. If it goes blank at any point, then it's more than likely your screensaver is set to on, so if you wouldn't mind just occasionally giving the mouse a wiggle, or just set it to off now. So here is the go to webinar dialog box. I'm sure you're fully aware of how you operate it, but if you do wish to minimize it, just click the red arrow in the top corner there, top left hand corner. You can ask questions at any point in time throughout the session, and we'll have a technical support engineer on standby to answer any of those questions. We are limited on time, obviously, as we always are, being half an hour, but we will respond to any questions either immediately after, or we'll just make sure to drop you an email. So we're just going to go through some of the webinar contents now. First of all, we'll give you an introduction, and we'll just look at some of the parameters of the bridge itself. Then we'll look at the basics of dynamic analysis, then the pedestrian bridge example, the workflow for dynamic analysis, the free vibration analysis, and the walking and jogging loads going across, creating the vibration shapes. And we'll look at the crowded conditions, and we'll also look at the peak acceleration limit check. So I'm just going to go through all of those. So just giving you a brief introduction. So dynamic analysis is the analysis under time varying external loading. So footbridges are often subjected to such forces. So we just focus on why dynamic analysis. So you talk about walking, running and jumping on footbridges, which produce dynamic forces which can activate appreciable vibrations. You could also look at the vibrations can cause discomfort to pedestrians and disorientation, so you can become rather sick if the footbridge is swaying from side to side quite excessively, and it can also damage the footbridge structural integrity as well, increase vibration. So we'll see during the presentation how to check the comfort criteria for the footbridges as per the Eurocode, and how to calculate the dynamic analysis effects on the footbridge itself. So we're just going to look at the basis for dynamic analysis. So from Newton's second law of motion, this time-varying force equilibrium equation is derived, which is the fundamental theory behind dynamic analysis. Unlike static analysis, which is dependent on one parameter called stiffness, dynamic analysis involves a time-varying force and consideration of three structural parameters, which are mentioned below. So we have the structural mass, marked out as M. We have the C, which is the structural dampening, and we have K, which is the stiffness. So F is the time varying external force applied on the structure, and XT is the time varying displacement, as you can see here from the equation. So the mass and stiffness are parameters which we are well aware of. The structural dampening effects and the amplification of the vibrations are all known as well. So the Eurocode recommends some values of dampening coefficient for different types of bridges, which are represented in the table on the screen. So today we will deal with a composite steel girder footbridge, which we've got as 0.04 as part of the dampening effect. I'll just continue. So this is today's example. So we are focused on a composite steel I-girder bridge for pedestrian live load only. The span of the bridge, or the types of supports as well, so the span of the bridge is 33 metres long. It is a simply supported single span, as you can see, and the number of main girders are 2, which are total spanning all the way across, and we've got the cross members, which are number 6. So just to represent those there, just show you quickly. Okay. So just going through the workflow for the dynamic analysis. So first of all, we must perform the free vibration analysis to obtain the natural frequency of the structure. This analysis will give us the most critical frequency of vibration and also the mode of vibration, which we will see in the next slide. The next step is to determine the pedestrian time forcing function. So the Eurocode suggests some load models to be applied at time varying force. These are different pedestrian scenarios on the bridge. So just moving on to the next one. So apply time forcing functions along the length of the bridge, maintaining constant pedestrian velocity. So the Eurocode load models are applied on the bridge with the co-specific constant velocity. So that is for that section there. So the final step is to check for acceleration time response to determine the peak acceleration at any point on the bridge. So the dynamic analysis in the software gives us the peak acceleration on the bridge, which can be compared with the code limit for comfort criteria. So just to go over where the code comes from and everything, so the analysis will be done as per the EN 1991-2 2003 UK National Annex 2.44, which calls for 2 distinct analyses. So we'll just go through those. So determination of vertical deck acceleration and a check for large synchronized lateral response. So now we're going to move on to the free vibration analysis. Just talk over this briefly. So a free vibration is necessary prior to any dynamic analysis. It follows basically the same equation without any external force or dampening, which is the equation you see on the screen now. This gives the natural frequency of vibration of the structure under no loading. So this frequency is a function of just mass and stiffness of the bridge. This gives us an idea of how the bridge vibrates on its own and which vibration mode can be the worst for the bridge itself. So the Eurocode gives a verification criteria that should be followed after the analysis, and a verification of the comfort criteria should be performed if the fundamental frequency of the deck is less than 5 Hz for the vertical vibration, which is in the Z direction, which we'll demonstrate during the software or during the use of an analysis for the vibration analysis. 2.5 Hz for horizontal and lateral or torsional vibration, which is in the X or Y direction. So now we're just going to go into the software. So just to drag the model across. So we have the Midas Civil working space. So first of all, I just want to tell you that we're not actually going to be modelling the composite bridge from scratch here, because we've already done that in a previous model, so in a previous webinar. Sorry. So if you do want the recording for that previous webinar so you can model the composite bridge, then please do send us an email or just give us a call and we'll send you the links. It's all on YouTube on our Midas UK page, so just to let you know that. But I'm just going to start this now and just go straight and just show you defining the mass and converting the self weight to mass, and also the other dead loads as well. So just using the structure type just straight away. So when we convert the loads to masses, just go down to load to masses and just do exactly the same thing. So we can just add different ones. So we can do it for the precast, the parapets and the bridge deck, everything like that. We can do it for all the services as well. So they've all been added to the structure. So we've got to make sure we convert all the loads to masses, and just to take the stiffness is taken into consideration because of the materials and also the sections, which are already defined. So I'm just going to show you the free vibration analysis. Now we can change the number of frequencies, so we can change that to 5. So now we just completed all of this section. We're just going to bring the post-processing module over, where the analysis has already been carried out. So we didn't want to waste time on the analysis. Now just go through the mode shapes and the vibration mode shapes. Now we've got different modes, so obviously you've got 1 to 5 there, and we can put a legend on it, look at the contours, and we can even do an animation. So there's mode shape 1, showing it heaving, and here's mode shape 4. It's a completely different mode. Now we're just going to show you an animation now, and then we'll show you some of the tables as well. So that's an animation, that is one complete motion. Now I'm just going to show you the table as well, just to show you how this actually compares up. Right, here we have all of them, so just to show you some of the columns. Now this is the cycles per second, so for every single second it will do 1.7 cycles, which is what I showed you before. So iterate up and down 1.7 times. So just to show you, this is one complete motion all the way to the very top. Just press play again, just find it. So all the way up to the top, then all the way back down, then back to the middle, and that is one complete cycle. So it will do that 1.7 every second. So let's just explain that for you. So here we have the motion in different directions. So you have it the sum of the mass in the first mode, which is the movement. So anything over 90%. So this shows what percentage of mass is participating by a given mode of vibration. And the mode with the highest mass participation is the critical mode of vibration. So as you can see for mode 1, which is over 90% or 92.1% in the trans Z direction, or the Z direction, which we'll demonstrate in the model now. So as you can see, this mode, we've seen it previously, we just want to see it again. So as you can see, it's actually heaving in the Z direction. I just want to show you by taking it back to the table, and I just highlight in the Y direction, so you can see it's 77.2%. And it's a cumulative, so it actually adds it up with each iteration. So we see that the cumulative mode 1, 2 and 3 will eventually be over 90% if you add all the modes up in the Y direction, just to show you the mode view in the Y direction for mode shape 3. So here's mode shape 3, just to apply it, and as you can see, it's actually bending in the Y direction. It's actually twisting in the Y direction. Okay. So now you must be wondering why I've only divided upon 5 modes, or decided upon 5 modes, instead of say 6, 10 or even 15. This is because the code says that the total number of modes to be considered for vibration analysis is based on the sum total of the mass participation of all the modes, so which we want to explain when you add them all up as you go along. So it should be no more than 90%, essentially. That's all you'll need to go up to. So you can see from the table that 5 modes here are significant, sufficient to give 90% participation of mass in the Y and also in the Z direction. That's another key factor for both the both the Y and the Z. The mode with the highest mass participation is the critical mode, which is the first mode, is the most critical from the vertical vibration, i.e. 1.79 Hz. So as per the Eurocode, we need to check for dynamic analysis. So I'm just going to go back into the presentation. Just load that up quickly now. So take you on to some animations. So that's the first mode, just showing you there, which is for the vibration natural frequency for vertical vibration is 1.79 Hz. So a check is required. So the second mode of vibration, natural frequency for lateral vibration, which is 2.95 Hz, which the check will not be required. Right, so after doing the free vibration analysis, which we just carried out, we will see how to apply external dynamic loads onto the bridge. To consider external force effects, we need to select a number of modes of vibration for the analysis. These modes should have a combined mass participation of at least 90%, which is what we covered previously. So if it does not meet 90%, the criteria, we have to run the free vibration analysis for more number of nodes. So the Eurocode suggests following dynamic load cases for comfort criteria, a comfort criteria check, and the walking pedestrian, jogging pedestrian, and also the crowding conditions have to be considered, and including the dampening ratio for the composite steel girder bridge, which is set at 4%, which we showed you briefly at the start. So for the dynamic models for pedestrian action, the first step is deciding the load model, which is selected for the class of the bridge, which has been nicely classified by Eurocode based on the type of usage of the bridge. Based on this class, Eurocode tells us what pedestrian densities should be considered in our loading. We will consider class B in today's example. So as you can see, N equals 4 for the group size and walking, and also the jogging is N1. Then we can also consider the crowd density, which is 0.4. So just going past that point to focus on the bridge uses. So we're talking about suburban locations likely to experience slight variations in pedestrian loading intensity on an occasional basis. So it might have crowd loading in a once in a blue moon kind of scenario. So just going on to the next slide. So we're just talking on the walking and jogging actions. This equation is given by Eurocode for engineers to calculate the dynamic force to be applied on the bridge. So the objective is to apply the worst case loading, and for that we need to make sure that we get a resonance condition on the bridge, i.e. the frequency of the loading should equal to the frequency of the free vibration on the bridge itself. We will obtain highly amplified acceleration vibration of the bridge. So ideally it's where the frequencies are coinciding and magnifying the actual amplitude of the vibration itself. So now we'll take you through the different parameters of this equation in the Eurocode. This code, as you can see in the table below, specifies unique walking and jogging velocities which need to be maintained during the analysis. So as you can see from the table, the reference load, or F0 or N for walking, is 280, and the jogging, which is 910. So just to focus on the walking and jogging actions in a different equation here. So K factor is an extra factor applied to make this equation meet realistic population situations. This involves pedestrian sensitivities to vibration and harmonic responses. So as you can see from the curve, so A is the walking, which is the solid line going throughout, and B is the jogging running, which is the dotted line. And you also have the most frequent, the mode frequency, and which is the bottom axis, the x-axis, and the y-axis, which is the combined population. K factor. So just going on to the walking jogging action, just looking at this formula again. So the function gamma is a reduction factor that caters for unsynchronized vibrations. So the y-axis of this graph represents the factor, the x-axis being the dampening factor for the bridge, and for the different spans you have to follow the black curves and note down the values of the reduction factor. So you can see the curves going along there. So just going to go into the software and show the time history, load case, and the time functions. So now I'm just going to drag the software over from my other window across. So I'm just going to focus on the time history load cases. So I'm just going to go up to load and load cases. Then we're just going to add a new one. So I'm just going to add the load case, just give it a name, which is walking, and just do the linear analysis, and also the modal as well for the analyst method. And then we're just going to change the end time, which is 20 seconds. This is the length of time it takes to go from one end of the bridge to the other. So what we say is the bridge is 33 meters long, the pace or the iteration is 1.7 seconds per meter, so it's an average of 20. It's going to take about 20 seconds to get from one end of the bridge to the other, basically. I think it's actually 18 point something seconds, but we're just going to stick 20 in for now. So it's going to change the dampening ratio, which we discussed earlier, which is 0.04 or 4%. And we just click OK. So now we continue. And similarly to this, you can create cases for jogging and also crowd loading. We're just going to stick with the walking in this scenario. But really for jogging and crowd loading, you just increase the amplification. So I'm just going to pull up my Excel sheet and show you actually the functions worked out. Oh, just got to drag that across. So as you see there, per seconds of time, the force changes. So we actually, this is the exact calculation that we had on the spreadsheet. As you can see, there's the force being produced as the time increases as well, and this is the forcing function going across there, the graph. So this one cycle takes 55 seconds, which you can see from the graph. 0.55 seconds. Apologies there. So that's one iteration, and there's the time and also the force. Now all we can do, we can copy and paste this, and we can select all, and just copy and paste this straight into Midas. We'll create a separate worksheet. So to show you the table now, we just go find it. So time history force function, just want to add it. You see there, we want to change it to a force instead of the acceleration. Then we can copy and paste the time and the function in there, and it also gives you your graphical representation. So we just call it walking. Click OK. Just close that. So I'm just going to go back into the presentation now we've discussed that. So we're just going to go for so how to apply these actions. So the load application points have to be decided and marked on the bridge, so we just put the nodal points where the pedestrian will be most expected to step onto the bridge. So the space of the points is in a manner that the constant velocity of the participant, as it were, suggested by the code, is maintained on the bridge, so making sure that the bridge is split up into equal sections. This is done using simple multiplication of velocity and time period of one step of the pedestrian. So the dynamic force from the previous slides should be applied on these marked nodes, and they should be applied at different time intervals. So marking the acceleration of the person going across the bridge. I've already calculated these in an Excel form, so just the intervals going across the bridge. So you can see here on the sheet we've got the different nodal points. You've also got the number of seconds that it takes to get over the bridge from one side to the other, so the arrival time, and then you've also got the scale factors in -1. So now I'm just going to bring over the model, and we're going to apply these loads into the table form. So we just look at the dynamic nodal loads, and we just got to create them first and foremost. So we're just going to select the node at the first point, just highlight everything. We want to create a node with a dynamic nodal load. So there's one node that's been created, or it's already existing, and we're going to use that node, and we're just going to put it in the Z direction and have the scale factor of -1, which we had earlier. So I'm just going to demonstrate this one more time, and then we'll use the copy and paste function to bring it in. So we just put in the number of seconds of the arrival time, and then we just highlight that second node, and that's how long it will take to get from one node to the other, which is 0.56 seconds. Now we can pull up the table, we can just copy and paste our Excel sheet into this table. So I just want to select from the two at the top down, because we've already got them in there. And just copy and paste those in. So now you see the dynamic loads are already applied, going across the structure. Now we're just going to go back into the presentation again. Move on to the next section. So we're just going to focus on the crowded conditions. Obviously these are slightly different. So this is the crowd load model defined by the Eurocode. The velocity should be the same as the walking velocity, and the crowd loading should be applied at the same time on the entire bridge. The direction of the force should be decided based on the most critical vibration mode shape. So here we have the pedestrian vibration. So we just run the analysis to see the vibration results, and these are the vibration results on the bridge structure. So the time history results for displacement for each time state, and also the max and min displacement acceleration results from the different load cases, which I'll show you now. So now I'm going to take you back into the model view. There we go, we just go look at the model view. I'll just look at some of the min and maximum displacements first of all. So just different, we can select the max for the walking, and we can just select some of the different values. So we just want to look at the acceleration and just click apply. So here we divulge the maximum, which is at 87. So we can just highlight that node for you now. So just put that in the node box. Obviously you've got the node box and then you've got the element box just next to it, and that node is in the middle, which is the maximum displacement. So now we'll look at the time history results graph and look at the displacements, and we can do this based on time. So we can click anywhere on this representation here and it will tell us the exact displacement going through all of the different times going across, and you can see the different steps just above the graph there, just telling you exactly where it is. So now that we've seen the displacement acceleration, now you're probably wondering what are we going to do with it. So what we really need to do is check the comfort criteria of the bridge. So I'm just going to take you back into the presentation and just show you that now. So just talking about the peak acceleration limit check. So the acceleration from the software is what we will use to check if the bridge meets the comfort criteria. So the limit of peak acceleration is decided by the code as shown below in this table, which depends on the number of factors. So just looking at K1, which is the site usage factor, K2 the route redundancy factor, K3 which is the height of the structure factor, and also K4 which is the exposure factor. And you can see all of these different factors in the chart below. So this is the peak acceleration limit check, and as you see you've got the time in seconds going along the bottom. We can also see that from the Eurocode is 0.91 meters, which is the limit, and we can see from our analysis we've carried out on Midas civil, which is 0.1. So it's a factor of 9 basically. So we don't have to carry it in. The check's okay. So just going to go back into the software and show you how we create this type of plot. Let's bring that across. So just look at the time history results and the graphs. So we just got to define that. So we look at the different cases. We want it just for walking, we just want to modify it. So we select the node number that we want, which is 6, which we've defined as being the worst case, which is right in the middle. And there we go, we can just identify that. If you not see, you can see a little purple dot right in the middle, and we want it in the DZ direction, and we want it for walking as well. So selected one of the low cases, so just by the walker, which is the vertical axis, and also the horizontal axis, which is time. So this is what our graph's going to look like. We just got to change the decimal points just to make sure we can fit it all on the graph. I just want to give the graph a title as well. So there you go, that gives us our graphical representation of the function versus time, and also our peak function, which is at 0.11, which we highlighted in the table previously on the previous graph at the bottom. So just talking about the vibration control. So now that we know from all of our analysis we carried out that our bridge is actually passing, but for vibration control these are some of the steps you can take. So you can increase the stiffness of the bridge. So increasing the stiffness is the best applied to bridges when the pedestrian vibrations are judged to border between acceptable and unacceptable. So the bridge structure could be stiffened in the appropriate direction, or the effective span can be reduced, so basically shortening the span of the actual structure. Significant design modifications may be required for this though. We can increase the mass. Increasing the mass of the footbridge will reduce the influence of human induced vibration, obviously adding to the weight of the structure. A proportional increase in stiffness is required to maintain the natural frequency, and significant design modifications may be required to carry this out, so you'll be effectively adding a lot of ballast to the actual structure itself. One of the most common used is the dampening system. So the dampening system increases the amount of energy that is dissipated by the structure. Mass dampeners can be tuned to specific frequencies, and viscoelastic dampeners can be added to cover a wider range of frequencies and motions. Dampening systems can be retrofitted to a footbridge after completion, so if it was a case of, like on the Millennium Bridge, when the vibration caused was far too much, then you can induce the dampening effect and add those to the structure like they did. For allowing for future installation of these devices in the overall design of long span footbridges is worth considering in some cases, especially in view of the difficulty in predicting the inherent dampening of these structures, making sure a full analysis is carried out. So we come to the end. I'm just going to close there. We haven't got too far over the time, but I'm going to call it a day on that one. So thank you for coming along to the webinar. I hope it's been very informative, and going back and forth between the model and the presentation has been quite frequent, so hopefully you've managed to keep up. My name's been Adam Kane, and thank you for coming along. We've got the details on the screen. If you do want to follow us on any of the social medias, we are on all of them. We are very keen on uploading content to YouTube and improving it all the time, so if you've got any suggestions, then please send them in. And yeah, we'll prove that. That's Midas UK on YouTube. So, but thank you for your time. That's absolutely fantastic, and I look forward to speaking to you and seeing you soon. Thank you.